A correct image prediction can still rely on the wrong pixels. Captum's Integrated Gradients traces the class score back to the input, so you can see what actually drove it. You'll see how to connect the pieces into a workflow that marks the pixels driving a prediction by comparing with a blank image. I'm Professor Pi, teaching AI foundations with simple Python. When a model predicts a class, the raw score does not explain which pixels matter. That creates two problems. First, you cannot trust the model for deployment if it looks at a watermark or border. Second, debugging becomes guesswork when a prediction looks right but for the wrong reason. Integrated gradients is one practical way to open that black box for image models built in PyTorch. And Captum gives us a compact implementation that plugs into existing models. The intuitive idea is simple. We ask how much the model's output changes as the image morphs from a baseline to the actual input. If a pixel causes the score to climb, it gets positive attribution. If a different pixel pushes the score down, it gets negative attribution. For a tiny toy image, you can see the important pixels directly. And for larger images, you get heat maps to guide further work. We will build a tiny experiment you can run in a notebook. It creates a small 4x4 image, a simple linear classifier that deliberately weights the wrong pixels, and then uses Captum Integrated Gradients to highlight which pixels actually drove the predicted class. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a tiny input and a baseline to compare against, so we can see how attribution measures the difference. This snippet creates a tiny PyTorch image and a matching black baseline, so we can measure attribution on a compact, inspectable input. The image is only 4x4, 2 bright pixels in the top row, and a softer square in the middle. Deliberately simple, so you can follow the math. Baseline is made with torch.zeros-like image, which gives us a true black reference. And setting requires grad equals true keeps the input ready for gradient-based explanation. The visible output prints total image intensity, so you know this is real data, not just a shape definition. Now that we have data, we need a model that can be inspected. A simple model makes the attributions easy to interpret. This transition shows why a deliberately simple classifier helps us see shortcuts the model might take. This example builds a tiny PyTorch classifier that can predict from the wrong visual cue. nn.sequential flattens the image and applies one nn.linear layer, so every pixel maps directly to a weight you can read. In this toy setup, Class 0 focuses on the center square, while Class 1 gives extra weight to the 2 bright top row pixels, so the model produces pred from logits even when the center looks more like the object. The printed prediction shows that logits alone don't tell you which pixels drove the decision. With a model and a prediction, we now ask Captum to explain which pixels supported that predicted class. The next snippet applies integrated gradients and extracts the strongest pixel, so we can see the shortcut in a concrete result. This code applies Captum Integrated Gradients to reveal which pixels supported the model's chosen class. The key call is ig.attribute, where img is compared with baseline and target equals pred focuses the attribution on that predicted class. Return convergence delta equals true adds a small sanity check on how well the numeric approximation matches the score change. After that, heat collapses the attributions into absolute pixel strength, and top finds the single strongest location. The printed output names the strongest pixel and the approximation delta, so the shortcut that lived in the weights becomes a visible explanation. A key modeling choice is the baseline. Changing it can change the attributions. So we will compare a black baseline to a gray one to make that effect visible. This snippet contrasts two baselines so you can see how the chosen reference alters the attribution magnitude. This snippet shows why the baseline image is not a throwaway detail in Captum Integrated Gradients. The same IMG, model, and target pred are explained twice, once against the black baseline and once against a gray reference made with torch.full-like. The important pixel location usually stays the same, but the total attribution size shifts because integrated gradients attributes the difference from the chosen reference to the input. A brighter baseline moves the reference closer to bright pixels, so the attribution mask can shrink. The printed percentage drop makes that modeling choice concrete. Finally, we turn the raw attribution tensor into a human-friendly heat map so a person can inspect the explanation visually. This final snippet converts the attribution into an image overlay that emphasizes pixels, pushing the class score upward. This example turns the Captum attribution tensor into a small visual explanation. Attra.squeeze detach.numpy converts the one image attribution into the image-shaped numpy array that viz.visualizeImageAttra expects, and the call uses method.heatmap and sign.positive, so the display highlights pixels that push the predicted class upward. Setting use pyplot equals false keeps the snippet friendly for notebooks, scripts, or automated tests where you may not want an automatic plotting window. The visible output confirms a compact heat map image layer was created, completing the tiny baseline experiment that shows which pixels drove the prediction. If you map this toy experiment to a real project, the heat map becomes a QA tool. Run it on a development set to catch cases where models latch onto logos, timestamps, or sensor edges instead of objects. Use the baseline that matches your deployment assumptions. And remember, baseline choice changes the explanation numbers, though not necessarily the top pixels. What it is: a gradient-based attribution that ties class score differences back to input pixels. Use it when you need to audit which pixels actually drive a PyTorch image prediction, especially to find shortcuts. One important caveat: attributions depend on the chosen baseline and on the model structure, so interpret numbers with that context in mind. A practical next step is to run the same workflow on the CFAR10 validation set. Compare a black baseline to a mean pixel baseline and measure how often the top attributed pixel falls inside the labeled object bounding box. That will turn the visual check into a measurable audit. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.